Chapter 11 on Angular Momentum. So some key points is that the angular momentum is the rotational equivalent of the linear momentum. And we define the angular momentum to have a magnitude and direction along the rotational axis and that the angular momentum is also conserved in the absence of an external torque, meaning that if you have the absence of external forces, so the angular momentum is conserved. And we're going to describe angular momentum in two ways. There is translational angular momentum and the rotational angular momentum. So let us now describe the angular momentum with the simplest point particle, which is a simple point particle, which is a point particle. And we describe the position of the point particle with a vector r with respect to the origin, and that this point particle is moving with a momentum p. And so, the angle between the two vectors would be theta. So now we can describe the translational angular momentum to be equal to the cross product of r and p. And the cross product is defined where the magnitude of r and the magnitude of p times sine theta. And if we blow up this image here, we have p theta and r. If we make an additional vector, which is that of r perpendicular, where r perpendicular is perpendicular to the momentum vector p. So therefore, r perpendicular over r is equal to the sine of theta. So then we can now redefine the translational angular momentum to be equal to r perpendicular and p, which is the magnitude of r perpendicular times the magnitude of p. So how do we find the direction of this translational angular momentum? There are two ways to do that. First way, there are two different types of right-hand rule. So in the first way, we can curl our fingers from r to p, which is, if you curl your fingers from r to p, from r to p, so we extend r. So I curl our fingers from R to P, then we have the translational angular momentum direction towards me. In the other method, you put your forefinger in the direction of R and your middle finger in the direction of P. So forefinger direction of R, middle finger direction of P, and my thumb, right, the thumb is the translational angular momentum direction, and that points towards me. So you either curl your fingers from R to P, so the thumb direction is towards me, that's the direction of the angular momentum, or you put your forefinger and your middle finger on R and P, and my thumb is in the direction towards me. So in the case of a comet orbiting, as the orbital motion of a comet, so suppose we have a comet that's going in a direction that's clockwise, then we can also use the right hand rule where we curl our fingers in the direction of motion, and the direction of my thumb is the direction of the angular momentum, and that's away from me. So in direction of angular momentum is away from me. But if the comet is rotating counterclockwise, then again, using my right hand rule, right hand only, will curl my fingers in the direction of motion, then my thumb points towards me, that's to me, and so the angular momentum direction is towards me. So let's take a look at the clicker question. So in this question, we have a comet orbiting the sun in elliptical orbit in the XY plane. So the red arrow indicates the momentum direction. So which arrow shows the direction of the vector R, where A is at the center of the sun. So the sun is the origin. So what is the direction of R? So from here, we find that this is a comet. Orbiting clockwise, the direction of P, and this is sun, the sun as the origin. So therefore, position vector RA extends from the sun to the comet. So your correct answer is number 8. That's your right answer. So coming back to the same example, we have again the comet orbiting the sun. So what is the direction now of the translational angular momentum? Knowing the directions of the position vector and that of the momentum vector. So we can use the right hand rule again, where R is my forefinger, and P, direction of P, is my middle finger. So with the right hand and with the right hand rule, we have now the direction of the translational angular momentum, which is that the direction of my thumb, which is pointing away from me. We can also use the alternative way of doing the right hand rule, which is curling the fingers in the direction of motion, which is clockwise. And so that also gives a translational angular momentum direction by using my thumb, which is away from me. So coming back to orbital motion, if we have, let's make an example where you have the sun, and we have Earth. That's Earth. So Earth rotates counterclockwise around the sun. Let's have some. And therefore, with the sun as the origin of the system, we have a position vector R in this direction. So there we can define the translational angular momentum of the Earth, right? Which is that. But the translational angular momentum direction is pointed towards me, where you curl the fingers in the direction of motion, or you can use the right hand rule, where R is the forefinger and P is my middle finger, and my thumb points towards me. Well, on top of that, we can also have the Earth spinning along its axis, which is omega. So this adds an additional component of angular momentum, which we describe as the rotational angular momentum. And so if the Earth is spinning with an angular speed omega, and we can also use the right hand rule, where we curl our fingers around the direction of motion, and so the translational angular momentum is likewise also pointed towards me. So we define the translational angular momentum to be the cross product of R and P, and the rotational angular momentum to be equal to I omega. So where I is the moment of inertia and omega is the angular speed. So let us look at this example and solve this example. So in this example, we have the Earth orbiting around the Sun in a nearly circular orbit. The Sun is at the origin of the coordinate system, and the Earth's orbit is in the XY plane. And we're given the position of the Earth with respect to the Sun, and the velocity of Earth, and hence the momentum of Earth. So what is the translational angular momentum of the Earth around the Sun? So let's calculate the translational angular momentum. So we can write the translational angular momentum to be equal to R cross P. So we're given the position of the Earth with respect to the Sun, and also the velocity of Earth with respect to the Sun. So we know that the position is given minus 1.5 times 10 to the 11, 0, 0, and cross product with the momentum, where the mass is given as 6 times 10 to the 24, and the velocity to be 0, 0. So So that's the velocity. Right. So if we remember how to do our cross products, is that if R is equal to Rx, Ry, Rz, and that P is equal to Px, Py, Pz, then R cross P is equal to, for the x component we have Ry, Pz minus Rz, Py, and for the y component we have Rz, Px minus Rx, Pz, and for the z component we have Rx, Py minus Ry, Px. So coming back to the cross product, we have now R cross P, and that P is equal to, so P is in the y direction and X is in, and R is in the X direction, so that's minus 1.8. So that gives us the final value of the angular momentum in the z direction.